I'm formerly geoscientist. I did earth science studies in the University of Madrid, but I was always interested in crystallography, and in particular in the interface between crystal and life. So basically, I consider myself as a crystallographer that explore the frontier between crystal and life, and in the last 10 years, also the frontier between crystal and art.
What is crystalline life? What does that mean?
As there is a sharp difference in terms of morphology between the behavior of morphological behavior of living systems, living organisms, and crystals. Basically, crystals are solid that they are polyhedral with the straight lines, with flat faces that never have, a sec. They make some microcrystalline structure, never have cues, they have sensuality in the shapes in some way, while life is completely different.
Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers, because once we do, we'll be able to put a donate button, and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD, and working on a product to help people overcome these problems, because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up, and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions,
common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. I have Juan Manuel García-Ruiz. He's a geoscientist, a research professor at CSIC, which means Consejo Superior de Investigaciones Científicas. It's at the University of Granada. We're going to talk about microfossils, crystals, giant crystals, and his other work. So, Juan, thank you for coming.
Yeah, hello.
Hello. Tell me a bit about your background and how you got into the work that you're doing now.
Okay. I'm formerly geoscientist. I did my earth science studies in the University of Madrid, but I was always interested in crystallography, and in particular in the interface between crystal and life. So that I consider myself as a crystallographer that explore the frontier between crystal and life, and in the last 10 years, also the frontier between crystal and art.
What is crystalline life? What does that mean?
Crystal and life, as there is a sharp difference in terms of morphology between the behavior of morphological behavior of living systems, of living organisms, and crystals. Basically, crystals are solid that they are polyhedral with the straight lines, with flat faces that never have, a sec. If they make some microcrystalline structure, never have cues, they have sensuality in the shapes in some way. While life is completely different, Life, everybody understand that there is a difference between the symmetry of life and the symmetry of crystal. So the symmetry of life is sensual, is curvature, is fractal behavior, while in the case of crystal, we have basically polyhedral Euclidean shapes. So are
you studying life that lives on crystals, or are you studying crystals and the origin of life separately?
Well, in principle, when people look for extraterrestrial signature of life, or when people are looking back in the rocks, seeking for proof of life, for evidence of life, what is we call biosignature, morphology is one of the main characters, to consider. Because in principle, it is considered that crystals, inorganic precipitation, inorganic crystallization, is unable to mimic the shape of life. And my investigation was about to explore if this is true or not.
Well, okay, so you said people will look for biosignatures on other planets. Are they looking for crystalline structures? Are they looking for, like, what is a biosignature versus just finding some repeating crystalline structure pattern?
Yeah, biosignature, there are different ways of biosignature. One of them is the isotopic signature of the material, okay? There is a discussion about if life remnants showed different signature of carbon and sulfur, and this is one of the main tools that we use to identify life elsewhere or life in the oldest rocks in the earth. But one of the main difference is morphology. So when people look for a structure that look like microbial, okay, so we are looking for, we know the typical structure in which you have curvature, you have some kind of rods, some kind of shapes that crystals are in principle unable to form. So this is one of the most important things that people are looking, for. So we're looking for biomimetic, for shapes that mimetic of what we know that are today microbial life.
Tell me about the giant crystals that you found. Like, where are they? And, what have you learned about them? I guess in caves.
Yeah, well, this is one of the fascinating investigation I did and still I'm doing, is the study of the giant crystals in different places of the world. There was the most famous one is what is called the cave of giant crystal of Nika in Chihuahua in the north of Mexico. This is a huge cave, with 45 meters, and there are different rooms, right? But in one of them is 45 meters by 20 meters, in which you can see is an empty space just covered, by giant crystal of 11 meter, of 12 meter. I say this is a cathedral of crystallography. This is a fascinating place in the world.
When was it discovered?
It was discovered in 2000. Actually, the Nika is a mine, very, very famous mine since 19th century. It's a mine for silver, for lead, and zinc. But inside this mine, inside the mountain, is a mountain in which you had limestone. Basically, it's a mountain made of limestone, but they have also some minerals called anhydrite, which is calcium sulfate. And in this system, there is a hot point below the mountain, below the range of Nika. And because of this hot point, there is dissolution of the calcium sulfate. And during the cooling of the mountain in the last 30 million years, okay, there was when the mountain reached the temperature of just cooling, reached the temperature of 58 degrees Celsius, then you start to crystallize gypsum. And then we found that this crystal of gypsum, as I told you, some of them 11 meters in length and 1.5 meter in width. This crystal were growing to very slow because they grow under the condition very close to equilibrium, and the growth rate is very slow. It's about 60 micron per. The cave is very hot. When we started the investigation, the cave was about 46, 48 degrees Celsius, but the most important parameter is the humidity. That was almost 100%. So every time we enter the cave to study the crystal, we can stay only for 5-6 minutes because we lost 2 kilograms of water every time we enter. So it was an investigation. It was very difficult, but it was fantastic. We really enjoyed this investigation.
Did you guys are you allowed to take samples of the crystals in there? Just pictures or, swabs of them? Like, has anyone sampled the crystal faces?
We were entering the caves. We studied the morphology of the crystal. We studied the fluid inclusion inside the crystal. We studied the isotopic composition of the crystal because the investigation was obviously to try to understand how this giant crystal formed. And then we explain the formation of this crystal based off a self-feeding mechanism of calcium sulfate dissolution and growth. And yeah.
What is the age of the crystals inside these big chambers, you think?
Well, the crystal of gypsum, it is impossible to measure because the purity is so high that the methodology that normally is used to measure the age, which is uranium isotope, there's not enough uranium to measure this. And therefore, we have to measure this indirectly. So we measure the growth rate of the crystals at the temperature in which we know they do, okay? And then we discover that the growth rate was the 60 micron per century. And then considering the width of the crystal, then we estimate that the age of the crystal, I mean, each crystal have a different age because everything happened very slow. So crystal form at different moments, right, in the history. So we estimate that the age of the crystal is about 200,000, 250,000 years.
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
When the mountain itself started to grow, like, or did the mountain form and then the crystals on the side of it formed slowly over time, or what do you think it looked like to an observer?
Well, actually, the crystals are growing now. So this mountain, the mountain of Nika, is full of caves because this is limestone system. So it's a karst, what is called a karst. So there are many caves there, and so the crystals are still growing now. So what happened is that because this is a mine, in order to harvest the crystals, the minerals, then you had to take the water out. You had to draw the mine. So we are able to enter in some of these caves because the miners were trying, the water. But in other places of the mountain, which have not been mining yet, which are located below 1 kilometer, still there are crystals growing there. So this is one of my aims, is to send to drill the mountain and to send a robot to study the actual growth of the crystal now.
So you said they grow how many microns and how long?
60 microns, in the thickness of a hair per century, every 100 years. Very slow.
Yeah, that is really, really slow.
Yes, wow. Very, very slow.
So the thought is like, go ahead.
Yeah, what is it? That actually we measure this growth rate as is the slowest growth rate measured so far experimentally, and we measure with a special microscope with a group of colleagues from University of Tohoku in Japan. Yeah, really, really slow, because this is why this is interesting, in addition of the beauty of this, because, it's something absolutely beautiful. But the main interest from the point of view of science is that the crystal grow under condition very close to equilibrium. So that in principle, it is impossible to make an experimental analog, because this is so slow that we don't have time to. So this is why
if you take samples of a crystal, some very old and some newer, can you analyze the differences? What could you see there?
It is impossible to know which are older than the other one, because as I told you, we cannot use absolute chronology. We cannot use absolute measurement of the age of the crystal. So what?
No, but within a single crystal,
yeah,
you must be able to tell, due to gravity, which way it grew. Like if you go and if you take a sample from the middle of it and one at the end,
Yeah, but this is not gravity. It's this. If you enter in this cave, it's a cave in which you don't have the crystal just pilot. The crystal are crossing the cave, So it's like a beam. The miners, the Mexican miner call the beams, and this is fantastic. So what we can do in principle, is possible to do it, is to make a cross section, and then we know that the outer part of the crystal are more than that the core of the crystal. Okay, but it is this is I think that will be really.
No, but the crystals aren't squares. I mean, they're long and somewhat narrow. So I know that the cross section makes sense, but if you can't tell which end, let's say you took a sample from one end and from the middle and then from the other end.
Yeah,
the crystal would, it may grow both ends. Both ends may grow equally outwards, but then again, it may grow in one direction. You know if they even do that, but you should be able to see some difference. If you have a 10-foot long crystal and you take samples from the middle and then from the ends, the middle, I don't know, does it grow in every direction?
Yeah, of course. The crystal are polyhedra, and then they are.
But why isn't it a sphere? Why is it more spherical? Why are they long and narrow, like daggers?
Because this is a good question. It's because the internal structure of crystal is periodic, three-dimensional periodic structure. So that it is by definition an anisotropic. Anisotropic means that the property of the crystal, the physical property of the crystal at different direction are different. So you have different growth rate depends on the direction. And this is the reason why the crystals are polyhedral. So the crystals are cubes, or they are hexagonal prints, or they are, rhombohedra. So this is how the crystal grow by a creation, of growth unit of molecules onto the different phases of the crystal, and the growth rate at different phases is different.
So what kind of cross sections have you been able to do? Like how thick are some of these crystals, and therefore how old are they at least with the cross section?
But the problem is that in any other crystal, you make a cross section and then you look at different position, different distance from the core of the crystal, and then you can measure the growth rate, the age. But here is so pure, because the growth rate is so slow that the crystals are very pure, and because of this is so pure, we cannot measure the age of the crystal. You know what I mean?
Well, based on the type of material that makes the crystal, seeing other crystals that you can figure out the age that are lesser purity, can't you assume how they grow? Like, don't you have a model or a heuristic how these things grow typically?
Yeah, I mean, in other material, for instance, calcium carbonate, or in calcite crystal, or in sulfide crystals, you can measure the age because there are some impurities, particularly some for a stable isotope that allow you to measure the age of the crystal. But in this particular case, in the case of gypsum of high purity, there is no a stable isotope that will, so you can use to measure the age of the crystal. So what we obtain, basically the information that we obtain from the inner part of the crystal is preserved in what we call, it's called fluid inclusions. So fluid inclusions are small bubbles of containing the water, the brine from which the crystal grew. Okay, with this we were able to interpret the condition at which the crystal were growing, in the past, and this is how our theory is mainly based on information obtained from the fluid inclusion inside the crystal. But this is a very challenging investigation.
Mm-hmm. So you've been in this cave? I see pictures of it. It looks amazing. It's like
amazing. It's absolutely amazing. Yeah.
Yeah.
So we studied there in Naica, and then we were also to El Teniente. It's a copper mine in Chile. And then also there is a beautiful geode here in Spain, in Almeria, in Pulpí, along with all the crystal in Spain, in central Spain, from crystal also of gypsum. All of them are of gypsum, crystal of gypsum, and all of them are fascinating. But Nika is, yes, by far the most amazing thing. Yeah.
Well, what did you learn from doing the cross sections? You said you can't really tell the age.
The cross section. The point is the following: is that when you found one of these fluid inclusion, okay, imagine little drops inside the crystal, and this drop contain the water or the brine from which the crystal grew. Okay, so then we look for fluid inclusion in different parts of the crystal in the cross section, and then you are able to know the temperature at which the crystal grew. So we know that the temperature was different at different level of the mine, okay, and that the temperature was different inside the crystal, so that the cooling, so you can see, with studying this fluid inclusion, how the caves, the water in the cave, the brine in the cave was cooling, with time. So this is why we made a theory on how this crystal grew and the growth history of the crystal. But unfortunately, we cannot really know the exact age of the crystal because we cannot apply absolute measurements.
Yeah, it looks like, the gypsum is made of calcium sulfate. So
Exactly.
There's no carbon to do radiocarbon dating. And I guess you said that you needed a uranium isotope.
Yes.
I think that's the one that has a half-life of 4-something billion years, but there's no uranium in it either.
There's very small amounts. So when we and other colleagues try to measure the age using this technology, isotopic studies, so we found the error bar, of the data that we found are huge. So we cannot really use this.
So the cross sections you took, there's no difference in the cross section either?
Different, yeah. Is this, as I say, what is you made a cross section of this crystal, you see that they grew. The same crystal, okay, the crystal itself was growing at different temperature in time.
How does it grow differently at different temperatures or with more or less moisture? What changes?
The temperature. So say again, please.
Depending on the moisture level inside the cave and the temperature, how does that change how a crystal grows?
Oh, yeah, this is important because this tells you the supersaturation at which the crystal was growing, and this influenced the nucleation because when in crystallization we have to consider two different things. One is the nucleation, so the birth of the crystal, and the other one is the growth. So two different, completely physics. The physics is completely different in both cases. So the temperature tells you the growth rate, and the probability of formation of new nuclei. But the difference is very small because the cooling rate was really, really very small. So that this is why we have very few crystals. Normally, if you go to gypsum deposit, you have billions of crystals. Imagine this. In most cases, you have caves in which the cave was filled with crystal, but there are millions of crystals because the supersaturation, the cooling of the chain of pH, so the parameter who triggered the precipitation did it very fast, okay? But this case of Nika and other giant crystal, other side with giant crystal, cooling was very, very small. And therefore, very few crystal nuclei per time. So that maybe in the cave of crystal, in Nika, the cave of giant crystal, there will be, let's say, probably 300 crystal, okay? I'm sure that each of them have a different age because this is absolutely unique place in the world. So you, for instance, you go to formation of crystal in lava, in a volcano, no? So you have a cooling, which is very fast, and they form billions of crystals, different minerals. In the case of Nika and Pulpí and in El Teniente in Chile, in this case, the formation of crystal is very small rate. So that you have very few crystal, and with time, this crystal can grow without interfering one each other. And this is the reason why we have this fantastic landscape.
The conditions inside Nika, have they been the same for thousands of years, or do the conditions change pretty rapidly?
Exactly. The condition for the last 250, even more, maybe 500,000 years, basically did not change. Only temperature was cooling, but 1-2 degrees every 100,000 years. So it is really very stable conditions. So we can have some changes, some just fluctuation, but not very big fluctuation in temperature and chemistry of the water.
Is there life on the crystals? Have you sampled that?
Well, the crystals are very pure, so we did not find life inside the crystal. There are some people who claim that they find, but it's had not been published. So what we found is we were looking we take sample of water very deep, almost 1 kilometer deep in the mountain, and then we found some bacteria that are there, but they are not influenced in the formation of the crystal. So this is a purely inorganic process. Nevertheless, there are miners working there since more than 1 century. Okay, so yeah, it's full of bacteria. You go there, and then you take sample. Of course, you will find bacteria, you will find viruses, right? But nothing that was crucial for the formation of the crystal.
Okay, how did the crystal caves begin, and how do you think they will end?
Well, you mean the formation of the cave itself?
Yes, the very beginning of it. How did it start, and how do you think it'll end?
Yeah, because you have a hot point in about 3 kilometers below Nika. So this is a very old hot point, and it was cooling with time. So when this in the Sierra of Nika 30 million years ago, start to have a magma that push the rock up, and this is why the mountain was formed. Okay, but the magma was unable to go out like a volcano, right? So it was there, and it was injecting very hot fluid in the mountain, and the fluid provoked the dissolution of the limestone, and this is the system, that is still heating the mountain, not too much, because now it's about 60 degrees, 55 degrees Celsius, okay? But this is what triggered the dissolution of the limestone. So the caves are forming because of the hot fluid that came from below. And then you have a system, of circulation of water, underground water, that is forming the caves, yeah. But at the same time that the caves are forming, there is a mineral called anhydrite, which is like gypsum. Gypsum is calcium sulfate with 2 molecules of water. And anhydrite is just calcium sulfate, no water, anhydrous mineral. So anhydrite is dissolved faster, okay, at low temperature. So that you are dissolving anhydrite and forming gypsum. This is what happened in there. This is also why this is unique place in the world.
Okay. Are there other features in the cave, things on the ground that are not the crystals, the walls, other rocks that you can date to see something?
You mean all the special feature there in the cave of Nika?
Yeah, are there other special features that can be carbon dated or dated somehow to see how old they are?
No, I mean, we study all the different minerals in the cave, and most of them have no relation with the formation of the crystal. The formation of the crystal is just due to anhydrite, the calcium sulfate, and nothing more. So there's no way we are trying, any new technology that is made available, we we try to use this with the crystal of gypsum. But there is no other way to study the actual age of the crystal. You can study the time of the caves, and the age of the caves, and the age of other minerals forming just earlier than the giant crystal, but not really. It is impossible to have more precise information about the age of the crystal. But the estimation that we make is rather good. So we are happy with that.
So what's the future of your research with the crystals? What are you trying to figure out now?
Pardon, say again?
What are you trying to figure out with the crystals now? Like, what is the new research that you're doing?
The problem of NICA is that this mine in 2015, this is as I told you, it's a mine in which is called a mine of water in some way, because you have to pull out water, to trap the water in order to have the miners, working there. Okay, so there was a depletion of water. The phreatic level, the level of underground water, was about 120 meters below surface. Okay, but then the mining, the front of the mine was about 1 kilometer, okay, below the surface. So it means that you have a depletion cone of water made by the mining company, okay, of almost 800 meters, okay. So imagine that the pressure in the walls of this depletion of water, right, was extremely high. And unfortunately, what happened in 2015, because there is pumping machine that are, extracting the water from the mines. And if you stop the pumping of the water, the level of water will increase about 4 meters per hour, okay? So, and in 2015, what happened is that there was a problem in the mine. There was a hole in which water started. This was the 1st of January 2015, and then the water start to enter the caves and enter the mining area, and then was just filled again back the water until the level. Unfortunately, they stopped in 400 meters, so that the clay of crystal, which is 290 meters in depth, is safe so far. But the mine now is not accessible. So we cannot really work too much. But one of my idea is to make like I call Puerto Nica, So the idea is that to go to this mine, there is a road. It's road inside the mountain. So it's a road, it's a tunnel of about 5 meters by 5 meters, okay? And this 5 meter radius, okay? And then you can go by car down until 1 kilometer depth, okay? So that now, if you go down, you use this road, this tunnel, you can go with your car until 400 meters, because 400 meters you will find now the water again, okay? So my proposal, but this is it's expensive, but it will be fantastic, is to make at that level, like a Puerto Nica, is to have there some robot, some submarines in which we will able to use submarine, coupled to Raman spectroscopy, X-ray diffraction, so to have some probe inside, like we do in Mars, similar to this, so that you can use this machine, to go inside and see for the first time how a hydrothermal system work, in situ. So that will be fantastic. This is my dream. I don't know if that will be possible. Okay. It is expensive, but this is a fantastic challenge.
Well, God forbid a graduate student wants to do their thesis on the age of the crystals. They'll never be done.
Yeah, well, the age of the crystal, the only way to do it is to have, all the new technology that we we make possible to measure the age with lower concentration of uranium or other stable isotope. Okay, this is one of the possibility, and the other one is to measure in very much detail, the fluid inclusion inside crystals. So yeah, this is the only way to do it. But NICA is a living, in some way, living hydrothermal system. Okay, it's a system and you have a hydrothermal properties. That means that you have water which is hot. Okay, and this provoking mineral reaction along the mine and on the mountains. Okay, and then that will be a wonderful possibility to use robot to study, how a hydrothermal system works on site. This is that. It will be fantastic. So let's see if this is possible.
Well, very good, Juan. Thank you for coming on the podcast. And where can people go to learn more about your work and to see NICA Cave and all this? Where should they go?
Sorry, say again?
Oh, where can people go to learn more about your research and to see the NICA Cave and the crystals?
Well, you mean all the project I have working now?
Yes.
Well, I'm working in a fantastic place. It's called Dalol in Ethiopia. This is a volcano. We just published a paper explaining this 2 weeks ago, and it is a salt volcano. You know that volcanoes are made by silicate material, by lava. Okay, made by silica because you have a magma. The magma go out. This magma is basically a melt of silica rocks, and this is the typical volcano. What we have in Ethiopia, in a place called the Danakil Depression, this is a place in which Africa falling apart. There is a brick. Africa is breaking. In what is called the Rift Valley.
Oh, really? Okay.
Okay. So in the place in which we are working is in the upper part of Rift Valley, in what is called the Afar Triangle. Okay, so there is a depression, which is Danakil Depression, in which the Red Sea is this area which is below the sea level. Okay, so in the last 250,000 years, there was many flooding, in different times, about 5-6 times, in which the Red Sea flooding this depression. Okay, they close again because this is a lot of volcanic activity. They close again, and then you have the evaporation of the sea water. So that because of this different flooding of the Danakil Depression, you have there a salt plain of about 250 square kilometers, okay, and 2 kilometers in depth of salt. So that there is a magma, there is a magma because all this area, you have the Ertale, a number of volcanoes there. So it's a magma below this area. And the magma is hitting this package of salt and forming a salt volcano. So it's a volcano with a crater, with lava, with a caldera, everything made of salt. And this is a fantastic place because in the hydrothermal system forming there, on top of this volcano, there is a palette of colors, a fantastic, I'm sure that you know Yellowstone, okay? So, and the color of Yellowstone, you have green, blues, blues, orange, red, yellow. Actually, Dalol means in Afar, Yellowstone, okay? But the difference is that while in Yellowstone and many other spring, and hydrothermal system in the world, the color are due to life, okay, to material, that are provoking the different color. In Dalol, we demonstrate that the color are purely inorganic process. Is that the spring that you have there in Dalol is a spring that the water is at 108 degrees Celsius. You have supersaturated solution brine of salt. There is no oxygen in this fumarole, in this water, in the springs, and the pH is hyperacidic, so it's a pH of about -1.5 pH scale, so it's below 0 in the scale of pH. So that means that it's about 10,000 times more acidic than Rio Tinto in Huelva. And also there is 30 grams of iron per liter. So that what happens is that the color is provoked by the oxidation of the and then you have a fantastic palette of colors, amazing. If you look in Dalol in internet, you will see the picture there. It's amazing. And also because salts, which is the most, boron system for crystallization, just pure cubes. I'm talking about the salt of the kitchen, the table salt. So it's cube, they are made of cubes, only cubes, right? But when you have the interaction of the crystallization with fluid dynamics, you will see in Dalol, we explain in Dalol the formation of amazing biomimetic. So you can see my biomimetic structure, so that forming at what I call a garden of mineral garden, It's amazing. It's one of it is beautiful, it is fantastic, but also a hell, because it's the hottest place in the world, the inhabited. So what is hottest place that has
how hot?
Yeah. Well, we used to can go only in December, January, February, because otherwise it's impossible. It's too hot. And then we wake up in the morning at 4, and at 11:30 we had to finish and to go out or go down, from the volcano, because the temperature starts to be 55 degrees. It's because there is no shadow. There's nothing there. There's no life. Actually, this is one place, is the only place known in the earth in which you have water and no life.
Okay. Well, very good. Juan, we're out of time. So we'll finish the podcast, but thank you for coming. And I appreciate all your knowledge about crystals and everything you described.
Yeah. Thank you very much for the invitation. It was a pleasure to talk with you.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.